is get through all of 9.2, which won't be a big deal. And parts of 9.2 bleed into 9.3. So the bulk of this is 9.2. I'm going to introduce a few topics of 9.3 as we go through. So that way you guys kind of get the idea of how all this is going to look. As you guys know, and we flipped our order this year in terms of how I wanted to try and work with rationals. And originally, obviously, when you say rational functions, we say, hey, this is just polynomial divided by polynomial. It's really all this is. And we've seen that because we've done the adding, we've done the subtracting, the multiplying, the dividing, the solving. We've done all that work so far. We've also done factoring. We've done finding zeros. We've done plotting points. We know directions. We know all of that kind of fun stuff because we've been working with polynomials for a little bit of time now, especially quadratics, polynomials, and so on and so on. So what happens here is that just this idea of what's called a rational function is basically, they write it out as f of x, because that's what we talked about. If you guys remember, it's called function notation. You guys remember that? So function notation is just saying that f of x is going to be p of x divided by q of x, where p and q and p of x, q of x are just other polynomials. Okay. Think of it as some weird looking equation divided by some other equation. Really all it is. You've been working with this. So what will happen here is we're going to talk about how do we graph things. Well, the way I like to start this is I'm just going to use something real simple. And I'm going to graph f of x equals 1 over x. That's a rational function. Where the numerator is a function, it's just 1, and the denominator is a function, x. When we talked about values in the denominators, we talked about what are extraneous solutions. Now, extraneous solutions are what is an answer that can't be an answer. It's basically what makes the denominator 0, if you will. What can't x be here? 0. So we know that x can't equal 0. If it was x minus 7, what could x be? Just little ideas. Now, what I want to do here is, you know me, I don't like graph paper. We don't need graph paper for a lot of the stuff that we do. We like to do rough sketches. Okay? And when we have what's called an excluded value, when we graph it as what x can't be, it's going to be an asymptote. Okay? So x can't equal 0, and anything that you have x equal a number is always a vertical line. So what happens is we get this vertical asymptote at x equals 0. Sorry that it's not straight, but you get the idea. Okay. When all else fails, move the graph. And like we've done in the past, what we want to do is we're going to make a table value of stuff to figure out what's going on with the graph. Let x, and it's going to be that it generates our f of x. Now, with this being an f of x is a fraction, I'm going to use positive numbers, negative numbers, and throw a couple of fractions in there as well, because you'll see it's really fast to work. For example, if I say negative 1/2, negative 1, we know 0 doesn't work, so we'll go to a 1 and 1/2. Now, as you're going through this, we've worked with this before. This is 1 divided by negative 1/2. Which means you take that bottom fraction, you bring it up, and you flip it. So what's 1 divided by negative 1/2? -2. So this would be, so if I'm looking at this just at negative 1/2, it's at -2. What's 1 divided by -1? 1. All right. What would be 1 divided by -2? -1/2. So at 2 would be -1/2, and so on, and so on, and so on. So on this side, you're getting this curve that looks like this.
If I do the same thing on the other side, you'll get the same exact curve, but going the other way. At 1, it was 1. At a half, it was 2. At 2, it was a half. Huh. What does that look like? Very good. It's hyperbola. We actually get a hyperbola here. Okay. Now, with this, excuse me, with this one, when you have rational functions, we're going to have basically graphing a bunch of different styles of hyperbolas. It's not like the conic section hyperbola where we did before. We had that center, the focus, center, vertex, focus, co-vertex, things like that, diagonal asymptotes. It's going to be a little bit different. In this case, it's rational hyperbola. They're still hyperbolas, but they have different properties. Now, as we go through this, what? Sorry. Sorry.
Oh no. No. I don't think I have to think about it.
That's fine. I'm an idiot. I'm okay with that. You didn't have to agree with me that fast. Anyway, so what happens here, we get asked, we have all these different, oops, sorry, I got ahead of myself. Will this graph ever cross the x-axis? No, it gets infinitely closer and closer and closer to it. Same thing with the vertical asymptote. It gets infinitely closer and closer and closer. Remember the, I'm not touching you, 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 I'm not touching you. You can get infinitely closer and closer and closer and closer and closer. So all these things have all these different properties. Well, what we're going to do is we're going to throw it right into the big bunch of mess. All right? Let's throw it into a whole bunch of stuff where we've got rational functions, and I'm missing some markers here. And we have, notice, A, H, and K. Ooh, horizontal shifts, A values, vertical shifts, all this stuff. So we have this, we're going to have different formats of these rational functions. One of which is this. Okay. Where you wind up with asymptotes. At x equals h, at y equals k. Bless you. Obviously, x equals h is the vertical asymptote. Y equals k is your horizontal asymptote. This is y equals a number. And this a value, as you will learn to see, helps us decide which quadrants things go into, but it's not a big deal. Okay? It works really, really quickly. So if I start with the idea of y equals -2 over x plus 3, I'll subtract 1. What I like to do is I always want to label out a, h, and k, and then I'm automatically going to plot my asymptotes first. Once you plot your asymptotes, then you know your boundaries that you're in, and you're just going to pick a couple of numbers on either side to figure out which direction the graph's going. And more often than not, you're going to get points that work cleanly. Okay. So if I take this, just move it. Oh, I didn't mean to. Did you guys get the idea? I basically just need to know your asymptotes are at x equals h and y equals k. So here, if it's x minus h, what is my h value? -3. What's your k value? -1. So a is -2, h is -3, k is -1. So if I go to rough sketch this, horizontal asymptote at -3, or excuse me, vertical asymptote at -3. A horizontal asymptote at -1. That's how I started. Now, when you go to pick points, you're going to want to pick points that are on either side of that vertical asymptote, because those are your x values you're choosing from. So pick, I don't know, 4.
Or pick numbers that'll look like it'll work out cleanly. For example, I don't want to use 4 because that gives me 7, 2 sevens. I don't want to work with sevens. That's not bad. But if I work with 5, what's 5? Or excuse me, what's negative 5 plus 3? What's negative 2 divided by negative 2? 1. What's 1 minus 1? What's occurring? I'm picking numbers that work cleanly. What's up? Think of it this way. The asymptotes have shifted from where our standard x and y graph goes to some boundary area, to the h and the k. It's moved your starting point to a different spot. Horizontal, vertical. Move things, in this case, it moved it to the right and down. So we took this and went to here. So, yeah, because now I know that I have a vertical asymptote at -3. So what I'm doing now, a little space here. I'm going to pick numbers on either side of -3 to substitute into the function to figure out points to plot. And I'm trying to come in my head what numbers are going to be clean. If I used, I'll go back and use -4. If I use -4, I said +4 originally, that's why I got 7. So I use -4. What's -4 plus 3? -4 plus 3 is 1. We okay with that? -1. -2 divided by -1 is 2. And then what's 2 minus 1? 1. So at -4, it is at 1. That's what I'm doing. I'm picking numbers that'll work. So at -4, it's at +1. I do the same thing with -5. -5 plus 3 is -2. -2 divided by -2 is 1. 1 minus 1 is 0. So with those 2 points shaped like that, that tells me the curve on the left is going to do this. That's what tells me. Just by having those plot points. Hello, Sleepy. Hi, how are you? Good to see you. Thank you. You can at least try. Won't kill you. I promise you. Now you go to the other side of it. Use -2 now. What's -2 plus 3? -2 plus 3 is 1. What's -2 divided by 1? What's -2 minus 1? There you go. So at -2, it's at -3. And now I go to use -1. What's -1 plus 3? What's -2 divided by 2? -1. What's -1 minus 1? And you see how that they're going up away from each other? That's how you're going to see how this one side is curving this way, the other one's curving that way. This just comes up here. And that's how we plot them. Start with the asymptotes. Pick points on either side of the vertical asymptote. 2 points on both sides. And you should get, whether it's the next 2 numbers or the next number and then another one after it, like 4 and 6, you might have to use just to make fractions and stuff work cleaner for you. Okay? Remember, even if I say this is non-calculator, I'll get you the dummy calculator. So you still have fraction marks, so you can still put stuff into it. It's just that I just don't want you to be able to go to the table and just write down points. It's too easy. Okay?
Now, back to the idea of like, that's not that gross, is it? I mean, it's gross, like, ish, but not like, yeah. I got it. Okay. The other style that I want to look at is like this. The other style that we look at, and I'll kind of see if I can reword this cleaner for you. Think of it as linear equation divided by linear equation. I think that's the easiest way to look at it. Okay, linear equation divided by linear equation. No exponents for this. Don't worry about exponential stuff tomorrow. These two guys share the same exponent. They're both to what power? 1. They're both to the first degree. Okay. So when you have first degree, or when you share the same degree, if you have polynomial divided by polynomial, you've got variables at the top and bottom. That means your vertical asymptote will be at x equals the leading coefficients, a divided by c. Whatever the leading coefficient is for both of those. Well, I'm sorry, I meant the horizontal. I was getting ahead of myself. Horizontal asymptote is at y equals a over c. The vertical is at the 0 of the denominator. Just like always, whatever makes the denominator 0 is going to be your vertical asymptote. Okay. Whatever the 0 denominator is always your vertical asymptote. And then once we get our horizontal and vertical asymptotes, guess what we do to plot? Exact same thing. We plot the exact same way. Now, one thing we didn't talk about in the last question was domain and range. So we'll bring that back into this one as well. So as we get into rational expressions, it's one of those things that they talk about. You ever heard of a thing called set notation? We've done it. Remember Jay Leno's face? The squigglies? So we'll go back to domain and range here again. All right. So let me show you an example of this. Graph paper. Y equals x plus 1 over 2x minus 4. And we'll talk about domain and range here in a second. So when you have this, you'll notice right away they share the same degree. The degree is the same in the numerator and denominator because they both have a variable. That means that the horizontal asymptote will be at the fractional, at y equals the fraction of the leading term coefficients. What's the leading term coefficient of the numerator? And what's the leading term coefficient of the denominator? 2. So you're going to have a horizontal asymptote at y equals 1/2. Where's your vertical asymptote? Vertical asymptote would be at x equals 2. Now, Hannah, what you're getting at, we'll get more than one vertical asymptote tomorrow. Today, we're just going to have singulars. We're not going to get too fancy. We'll do that stuff tomorrow. So, again, that's going to be our starting point. That's going to be our little boundary area for where we're going to plot points. So we go to we make a graph. Please make a larger graph than what you guys, don't just do on your homework, go, Murphy, I did my homework. First day, ladies and gentlemen. So we start with this. Put your vertical asymptote in. Vertical asymptote be at 2, so we just go over 2. Horizontal asymptote is at 1/2. So in my mind, I'm thinking, hey, some good points to pick. 3, 4, 1, 0. You see that? 2 to the right, 2 to the left. If I use 3, I get 3 plus 1 over 2 times 3 minus 4. What's 3 plus 1? 4. Very good. What's 2 times 3? Subtract 4. So we get 4 over 2, otherwise known as 2. So at 3, it's 2. Sir. You're okay with the vertical asymptote at 2, correct? Yeah. So what I want to do is just pick numbers on either side. All I'm doing is just picking the next 2 numbers. Remember when you first learned how to graph lines? When you first learned how to graph lines, y equals 2x minus 3. You knew that that was going to go through it's going to cross the y-axis somewhere. When you did that, you picked values of x. You probably did -2, -1, 0, 1, and 2. That was kind of the standard way most people taught how to graph functions, because it's going to cross the axis at some point, so figure out where it crosses it, and then pick points on both sides of it. Think of this asymptote as the shifted y-axis, okay? So once I know that that axis is at 2, what's the next number to the right of 2? 1. It gets in the middle of the yawn there. So I got 3 and 4. What are the 2 numbers to the right of it? 1 and 3. That's all I'm doing. All I'm doing is picking arbitrary numbers that generally will work clean. You can pick 17 if you want. You can pick -4. It doesn't matter. It doesn't matter. But the closer you pick your values to the guys, this is a good point here. The closer you pick your points to the asymptote, the better you're going to see the direction quicker. Does that make sense? I'm not just pulling a rabbit out of my hat here. If I use 4, 4 plus 1 is 5 for the numerator. 4 times 2 is 8. 8 minus 4 is 4. So you get 5/4. 5/4 is a smidge more than what? 1. So if I'm looking at 4, I go to a smidge more than 1, what direction is this moving in? Yep, it's moving down and over. Then that's what you'll be able to tell. So one side's doing that, which means if we do the numbers correctly for the other side, they should mirror it on the other part of the asymptote. So I use 1. This is going to be tough now. 1 plus 1.
I don't know.
No, it's not too hard. It's just 2. T-O-O is different than T-W. No, T-O-O. Hi, Hannah. Yeah. I want 2 points on both sides. I don't want anything because it's other than that. After you get 2, it's all you need. 2 gives you direction for this hyperbolas. You don't need the extra points. There will be other graphs later on that will do multiple points, but for this, all you need is 2 on both sides. So we had 2 over 2 times 2 minus 4 is -2. So at 1, it's -1. You guys get -1 for that? And then you get 1 over -4, -1/4 at 0. So at 1, I'm at -1. At 0, I'm at -4. So I should be doing this. And there's my graph. A quick little table, 4 points. Plot your 2 asymptotes. Draw your curves. And that's what we're looking at. Okay. Let's try it. We'll do one more of each style and then we'll call it a day. Look, 2 examples of both. So I have y equals -1 over x minus 4, all plus 3. So this gives us y equals -1 over x minus 4. Just where's your vertical asymptote? Four. What can't the denominator be? 4. Where's your horizontal asymptote? 3. Which means I'm going to pick numbers on either side of that vertical asymptote to substitute in. And like I said, sometimes you get decent, clean numbers, sometimes you get crappy numbers. So if I use -5, yo. Oop. Sorry, I didn't even realize I did that. Sorry about that. I didn't realize I wrote the negative. I was looking at the negative. I just accidentally wrote that through there. So the 0 for the denominator would be +4. So I have an asymptote at +4. I still have a horizontal asymptote at k, which is 3. So now when I pick my values, I'm going to pick 5, 6, 3, and 2. Numbers on both sides. Okay. So let's see. 5 minus 4 is 1. You get -1 divided by 1 plus 3, which is 2. I'm hoping. Been known to make dumb mistakes before. -1 over 2 plus 3. 2.5. Well, that's good because that means that it moved up, so it's doing this. I use 3, I get -1 divided by -1 plus 3, which is 4. And then -1 divided by -2 is 3.5, which is good. So it's doing this. It's a good sign that you can get it to mirror themselves out. Don't let the arithmetic be a barrier. Use a fraction bar on the calculator if you have to, and just press some buttons. Okay. Just don't use your y equals in table, because I won't let you use that. Use that as a fraction. Okay. One more like that then? Yes or no, either way, maybe. you know, we didn't talk about domain and range. We'll do domain and range with this stuff tomorrow. We'll add it in tomorrow. No big deal. Don't worry about it yet. If I ask you about domain and range, I'll re-show you all that stuff tomorrow with this. With the homework, we'll go back and use that as our how do you state domain and range from what you did, and then you'll see, oh, that's really easy. So when you see this style, remember, when you have the same degree of numerator denominator, that means your your horizontal asymptote will be at the coefficients fraction. So here you've got a horizontal asymptote at y equals 2/3. Your vertical asymptote is at x equals 3. If x equals 3, you get 11. Negative 2/3. Subtract 2 divided by 3. Remember, set the denominator equal to 0. The vertical asymptote is always going to be at the 0 of the denominator. Okay. Sir.
Oh, I'm just stretching.
Good. Didn't want to talk to you.
Okay.
Hey, I'm trying not to pick on Hannah, so I gotta spread. No, I didn't pick on. I was trying not to talk and have fun with Hannah, so I thought I'd talk and have fun with you.
I'm fine with that.
How do you graph 2/3? Well, you put it somewhere a little bit more than halfway. You call it a day, right?
Okay.
I'm a poet and I didn't know it. So for this one then, values you'll pick 0, 1, -1 and 2. If I use 0, what's my y value? 1. Very good. That's nice. Nice and clean. If I use 1, I get 4/5. Is 4/5 bigger or smaller than 1? Smaller. Now this is the downfall when your numbers are very close to the asymptotes, and see how the asymptotes are right next to each other, kind of, or I would say right next to, but they're the range between the x values and the y values are kind of small for where the asymptotes would be. This is just a little bit smaller than 1, which means it has to do this. That's the only downfall sometimes of picking really close numbers. I should have used like a half. You know, that would have spaced it out a little bit more. If I use -1, my numerator becomes what? 0. My denominator does not, so that's good. So I know that -1 is at 0. That's convenient. If I use 2, what is it? 6 in the numerator, 8 in the denominator, 6/8, so 3/4. Does that sound right? And 3/4 is up here. Oh, thank you. So this was. I should write this down. I did write it down. So -4 plus 2 is -2. -6 plus 2 is -4. So that's at a half. Well, that makes more sense. Because 3/4 would have jumped the asymptote and now we're back. Oh, yes, it is fun time. All right, let's do these. So this is what's 9-2.
when you plot these, asymptotes, write them down. 2 points on either side, so you should have 4 ordered pairs. Does that make sense? Each one of these will have 2, they should all have 2 asymptotes, 4 ordered pairs. I'm trying to make sure you guys just go into detail on this, start, and then we can piecemeal stuff together later. We'll worry about domain and range on this tomorrow.